with exploration 4 then, we're looking at being able to write standard deviation in a slightly different way. So standard deviation being the sum of each value, its difference from the mean, squared, divided by how many values, and square rooted. We've been through that lots of times now. So you're now going through a process of putting it in a different way. So to start with, it says expand the brackets. So you ended up with x squared minus 2x mu plus mu squared, yeah? So you've got sum of that still all over n and still square rooted. Happy with that, yeah? Then it said distribute sigma. Okay, so that means we've got the sum of x squared, okay, minus the sum of plus the sum of T-back. Sorry, missed it.
In the book it says that is 2 plus. For example, plus. So
Yeah.
I think they just put the...
Yeah, but actually you'll see it doesn't matter. Adding a negative or subtracting. It's what we do with it at the end. So sorry about my line. Still got that. Right. Then we have to split the fractions up. So this is like having 3 fractions added together. So we've got the sum of x squared over n minus the sum of 2x over n plus the sum of mu squared over n, still square root. So we're just following their examples. You all happy enough with all that so far? Okay.
That's where I got stuck a little.
Okay, so then it says substitute in a couple of things. So it's telling you to substitute in, one we know, that mu, the mean, is the sum of the values divided by n. So we've got to replace that. We'll just do that to start with. So that is anywhere where there's the mean symbol, we can replace with that. Okay, but we've also been given another one, and note the way around it is the sum of mean squared divided by n is the same as that. Yeah.
How does that work out?
Say again.
How does mu squared to the sum of mu squared?
Do you know what? I spent a long time trying to prove that, and I can't. I need to look into it because I don't agree, but they've told us to do that. Maybe it's something that comes in it. I'll be honest with you. All right. This, I was trying to get this from the previous. So I spent a good couple of hours going through these 2 explorations, and the first one I thought would lead, well, I understood this one, I thought it would lead to that one, but using exploration 4, I could not prove that from that information.
I thought that instead of having the mu, there should be an x.
But that doesn't work for then what we want to do. But I get what you mean, yeah. All right. So what we're going to do is we're going to do those substitutions. Does that make sense?
Yeah.
Okay. So any ideas?
The third fraction can be substituted with mu squared.
So this one, yeah? So that is the same as that. So we can swap that one for just mu squared. No? Yeah? So I'm substituting in. So I've still got my square root sign. And I'm saying that this here is the same as that there.
Yeah, sure.
So I can replace that with that. So that's what I've done.
Yeah, makes sense.
Eva?
For the second price.
Hang on, not yet. If you're giving us more, I just want to make sure everyone's happy with that, yeah? Are you all...
Yeah. Is it always just going to be like whatever that is
So what we're doing, let me tell you what we're doing. What we're doing, like I said, we're trying to go from the way we've worked out standard deviation before. What they're doing is they're leading you through the mathematical process that was gone through to show that actually we can work out standard deviation in a different way, using different numbers. And they're showing you how they've gone from one equation, one formula, and they've done some substitutions to show how it can actually be represented in a different way. That makes sense? So this is not something you always have to do. This is just something to show you where it comes from. You won't need to do this process all the time. However, the maths that we're going through is something you should feel that you can do in other situations. But you don't need to memorise all of these particular things, but what we're doing you should feel relatively comfortable doing. Does that make sense?
Yeah.
So what we end up with will be still for standard deviation, but in a different form, using different things. Yeah? So what we've been given is this one we've been given, and we've been told that if you've got anything like that in your formula, which we do, you can replace that with this.
Is that like a rule?
That is what's called an identity. So you can always replace. It's like saying if I have a 1/2 written, I can replace that with 0.5, can't I?
Yeah.
I can always do that, can't I?
So,
Is that a rule?
no, you don't have to.
Well, it's
So it's
a
a
rule that you're
possibility.
allowed to.
Well, that's it, isn't it? Yeah. So
It's a rule you can, but
they are equivalent, aren't they? So you've got to be careful with the word rules and things. You know, it's not like saying you have to do this. This is something you can do. All right?
Well,
You are allowed to replace this thing with this thing.
so 100% of the time in the standard deviation equation, the sum of the mean squared over n.
Right. What I want to do,
is mean squared.
this is what they're telling us. But I need to look into this a bit more because my understanding of this statement did not work with the numbers they gave us with exploration 4. But I am going with the fact that they've told us we can for this exploration, and I'll come back to you if I can find out some better explanation. It's not in this book as to how to do it. So, and like I say, me and Mr. Cunningham were looking at it thinking, where's this coming from? But we need to look into it. Yes?
Doesn't that only work if there's one instead of like one data? Like if there's only one number, one n. Because otherwise it's the same thing but divided.
But do you remember we were looking at the previous explanation that finding the mean of two populations?
Yeah.
We worked out the two separate means, and we showed you couldn't just add those together to get and divide by 2 to get the mean.
Yeah, because there's different.
So this comes from the fact, I think this comes from the fact that you can't just add the means, but you can add the squared means and divide by the total number of numbers you have. And that will be the same as taking, remember we did the square of all the values and dividing by the, so this is like having it as 2 separate populations or 3 separate populations, but dividing by the total number. You can just add the square, and this would be just doing it in one block of numbers. See, like we did with exploration 4. The only problem with that is I couldn't make that work with the numbers they gave us in exploration 4. So I need to check. But they've told us that is the identity. They've told us we can. Yeah? Right. So the big thing I want from you is, though, to understand that if we are told that these two are equivalent, you can do this substitution. Right? So the other substitution that we are told we can do is the fact that this here can be replaced by... Okay. Well, what I'm going to do, though, we're always going to work... because that's what they've given us, this direction. So this can be replaced by this can be replaced by this. So, where are our mu's? Well, we've already got rid of this one, so the only one we've got left is here. So that is going to be replaced by sum of x over. Yeah? So then we've got, the first one we haven't done anything with that. So then we've got subtract the sum of 2x, sum of x over n and over n again. So n squared.
Yeah.
Yeah? Because mu, remember, got replaced. So let me explain it maybe a little bit better. So I'm going to get rid of it like that. And before I do that, I'm going to replace this. This, if I split it up again, this is like doing the sum of two lots of x. Are you okay if I write that as two lots of the sum of x?
Yeah.
The sum of two lots of x or two lots of the sum of x is the same thing, right? That is multiplied by mu. Yeah? And if I put that as over n, but this is just over 1, are you happy that all of that is the same as that? Because when you multiply fractions, you just multiply the tops, multiply the bottoms.
Isn't the mu is also with the sigma?
Yeah, so I've got the multiply, I've not separated with a plus. Yeah, that's, yeah. All right, so I've just split it out so you can see that then if I do this, then I multiply by, instead of this, I can now write this. So this bit here has been replaced by that bit there, yeah? Wonderful. Can you see that? Yeah? So that one there. So I've literally, when we're saying substituting, I've literally just replaced that mu with that the thing they tell me it's the same as. Yeah? Don't nod your head if it's not the case that you because that's quite a basic, fundamental thing of maths. Like, if I say to you one thing is equivalent to another, and then I say, are you happy that I can replace that with that for that reason? You have to understand that is a very big fundamental within maths, that things can be replaced. Yeah? They mean the same thing. We'll give the same answer.
Still a minus, right?
Yes, I haven't put it in.
Okay, so it'll be two lots of sum of x. Multiplied by the sum of x, so all over n squared.
Okay, so what I've got to do now, okay, is I need to look at this bit. Now this bit I can simplify as two lots of the sum of x over n squared. Got that? Because this multiplied by itself yeah? Is that all right? Anything multiplied by itself, put it in brackets. So you see how the sum of x gets multiplied by the sum of x. So it is the sum of x squared. So that's why we did the expression to understand what that sigma notation means. So the sigma notation means take all those x values and add them up. So the sum of x is just a number, right? Whatever all those x values are, you've added them together, you end up with one number. And you do that and multiply by itself. So that's the sum of x squared. You're right, it's not the sum of squared x squared, yeah? Because that doesn't make any sense, right? The sum of squared x squared. So I wouldn't. That's quite important, yeah? Yes? No, I need some kind of response. Some of you like lost kittens and rabbits in headlights and things. Yes? Please don't ignore me and think, I'll get it next Christmas. Santa Claus will bring me osmosis knowledge. No? Alright? Okay. So, currently then, my formula is now the sum of x squared divided by n minus 2 lots of the sum of x divided by n squared plus the mean squared all divided by all square rooted, and this is still the standard deviation formula. Okay? The next step, it gives us another thing which says substitute in again that mu equals the sum of x over n. Alright? So we've got to substitute it in again. And that's basically because I've gone from here to this one, and then this one needs to go back to this. I'm trying to, are you seeing what they're trying to eliminate from the formula? The mean, yeah? Is that what you're going to say, Tatum? Yeah? They're trying to get rid of the mean. So this is this, so we've then got mu squared is equal to this, but then it's also equal to the sum of x divided by n squared. Okay with that? So which bit am I now replacing? The last bit. Okay. So I'm now getting rid of this and putting that. So that then gives me the sum of x squared divided by n minus 2 lots of sum of x over n squared plus the sum of x over n squared, all divided by, or square rooted, sorry. Now we can collect some like terms. Just extend the page. So, what are the like terms? Tatum? The last two. So, what can they simplify to?
3 brackets, the sum of x plus n squared.
Not quite. And this is why when Thibaut asked me why it wasn't -2, and I said I wanted to put the subtract rather than the -2. So it's minus 2 lots of it plus, so it's not 3.
No,
Negative sum of x.
Yeah, so it's -1 lots of this now, isn't it? So we get the sum of x squared over n, subtract, well I've got -2 of them plus another one, so it's just -1 of them, all square rooted. Okay? And that, okay, that is standard deviation, but in terms of what we call summary statistics. So what do we have in that version of our formula? No mean, right? And what you'll have is what you may have noticed when you used your graphical calculator. There are 2 values in there that we'll use that your calculator will show on its screen. The sum of x comes up on its screen, and you might think, well, why do I need that? Because I add them up anyway. Why do I need that as a separate thing? It's done that already. But actually, now we've got that, we can plug it in here. And on your calculator screen, when you do your one variable statistics, you will also get the sum of x squared. Right? And you'll also get the other things. You'll get the standard deviation, you'll get mean, median, not mode, but mean and median, and you'll get the quartiles and all that. But you get these two appear. It's like, well, why bother? Well, that's because we now have another formula for standard deviation. So just to summarize, the first one we had was the sum of x minus the mean squared, all divided by n, square rooted. And we also have another version now, which is the sum of x squared divided by m. Do you remember doing that for the exploration 4? They said now find the mean of all the squared values. So that's that bit. Right, and we subtract the sum of x over n, which is the, what's that also known as? The mean, but that's squared. So that is now a second formula. Yes?
If on your calculator you get the mean and the sum of x and the sum of x squared, would you recommend just using the first formula? Is it easier?
Well, what I would say is all these formulas can be interchangeable. You can use any of them. Some are better in certain situations. You need to pick the right one for the right situation. So, for instance, if I take it back to what is the equation of a quadratic curve, you've got different forms of quadratics, haven't you? You've got the standard form, you've got completed square form, you've got factorised form. Which one do you use? Well, you use whichever one fits the information you're given. Yeah? So what I want to have a look at, that's why I want to go through, what we need to do is look on, can you look on page 89, and let's see with example 4 how we would use this information. So I'll state again, what we've just gone through is not something that you're going to be expected to reproduce in an exam or anything. I am not going to test your ability to specifically do what we just did. However, your maths should be at a level to be able to do that in any situation, with any equations or any formulae, right? And as you get better, you'll get better at doing it. What you do need to do in this particular context is be able to use those formulas, all right, for standard deviation. So let's have a look at example 4 as to why we might want to use it. All right, are we ready to move on? Are we okay?
Yes, ready.
Well, they're on page 89, the pink box at the top of 89. Yeah. So let's have a look at example 4. Right. Let's have a look at example 4, and it says the length of time t in minutes for a skier to travel down a mountain follows a normal distribution, okay, and is recorded on 15 runs. The summary statistics are, okay, the sum of x is 129. Now, what does that mean in terms of this situation?
All the x values equal 129.
But that's a generic situation. What does it mean in this situation?
This situation, there's a time in minutes. It takes to travel down a hill. That's the sum of all of the times.
That's the sum of all of the times, yeah. How many runs did you do?
15.
15. Right. What have we not been told?
You haven't been told how high the hill is, how many
Well, think more specific about the times. 15 times.
What they are.
What they are. We haven't been given the individual times. What we have been given is the sum of those times. He took 129 minutes to do it 15 times. Okay? And then we've been given the fact that the sum of the times squared, right, is 118, which is my sale number, funny enough.
Really?
Yeah, exactly that number. The number of the sale for my boat.
Yeah, it's like what they use to identify you in a race.
Yeah, I am GBR 1181. So it says find the mean and standard deviation of the times taken for this e-run. Okay. So the mean is
129 divided by 15.
yeah. So it's the sum of x divided by n. So that's 129 divided by the 15 runs, which we can see is 8.6 minutes. All right. I'm just copying out the example from the book, just in case you're wondering where I get this from. All right. The standard deviation then. Well, what options do I now have? So, for instance, Tatum, could I use this formula?
You. Yes.
Okay. Does anyone disagree?
I disagree.
Why do you disagree?
Well, I might be disagreeing for the wrong reason. I just think it's harder to do that.
Oh, well.
Ah, but that's not what I asked.
Yeah.
Harder is not impossible. I asked
Yeah.
whether it's possible.
Yeah, I know.
Can you use it?
Actually, we don't know what x is. We just know the sum of x.
Yeah.
I don't
Yeah.
know.
So that formula, does that not involve us actually,
Unless.
Knowing.
we need to know the difference of every point from the mean and then we can add that up. Yeah? We don't have that.
Because you'd have to then do the steps we did in exploration.
So we, having already done our rearrangement, now know that actually we can do the sum of x squared, keep going back to the sum of x over n squared and square root it instead. Do I have that information?
Yeah.
Yeah, so that's what I'm going to use. So I now have the sum of x squared over n, so that's 1181 divided by 15, subtract
Squared.
8, you're happy if I put 8.6?
It's 1181 squared.
No, I've already, this,
No, it's 1181 over 15 times 15.
no, look at the formula. It's the sum of x squared, which is what I've been given, divided by n, the number of runs,
Yeah, that's 15.
which is 15.
And then the next one is
This, the sum of x over n is the mean squared. Now I've already worked out the mean, 8.6 minutes. So rather, go on.
Squared in the book.
What 1181 is the sum of
Yeah.
x.
I don't know why it's squared in the book.
No.
Must be a misprint. No makes no sense.
Yeah. Well, let's work it out. Let's just check. Do we? And then we have to square root. Do we have to? Equals what? Okay. And that's what they get. So obviously, that was a misprint in the book. That extra little squared. I haven't even spotted that. To be honest.
Wait, did you do the square root?
I just read what it said.
Oh, should we check then?
It's right.
It's right, yeah, without the squared, extra squared, yeah. Okay. We've got 2.18 minutes. So we've got the standard deviation. It says, now, this is the bit that you guys find hard. And I think you try and overcomplicate what can be said. And when you're trying to find too much to say, you start making stuff up that has no relevance or evidence, if you know what I mean. So look at what they've said for their make a generalization about the times for the ski run? Right, do you know where that comes from?
Yes.
Yeah.
Where does the 68% between those two values come from? Dayton?
Well, what we were doing the other day is you take the standard deviation away from the mean.
Yeah.
Or from the mean, and then you add it, and then that's the normal distribution.
Good, I'm glad you said that. So in in the question does it say that I'm allowed to consider it normally distributed?
It says
Oh, yeah, it does.
follow the normal distribution.
Exactly. So you've got that piece of information. So you now know, just from that line, that if I know the mean and I've got the mean plus one standard deviation and the mean minus a standard deviation, there should be 68% of your data between that. So we now know if the mean is 8.6 and the standard deviation is 8.6 plus 2.18 and 8.6 minus 2.18, okay, that should be 68% of his ski runs. Should be. I mean, it definitely is, but should be.
Well, it said it follow normal distribution though, so it doesn't mean that it is. Or
Yeah. What I'm kind of getting at there is, will it be exactly 68%? So for instance, let's work out how many runs that actually is then. How many of his runs would fall between those two times?
Well, 68% of 15.
Yeah. So we reckon 68% of 15. So what would that be?
0.2.
Times 0.2.
Go for it. You guys with calculators, not me. Half of you, put them in your bags.
10.2.
10.2. So what would you say? 10 runs? 11 runs? That's what I was saying about should be 68%, but it can't be exact.
Because you can't have like 0.2.
Exactly. So we could say either 10 or 11 of his runs should be within that time. All right. Now, what I wanted to get at is what is not in that statement. When it says make a generalization about the times for his ski run, what is not in that generalization? Yeah? Yeah, it's not there. Well, it is there because it's in the 8.6 is there.
Number of ski runs.
Well, that's part of it. What? Maybe I'm not explaining. Remember I said to you, you start saying things that there's no basis of evidence in. All right? Remember I said that about your last projects and things. You have to stick to the evidence. Remember I said that sometimes you try and say more than you need to say. They say make a generalization, and I'm saying look how short that is. What they haven't written is anything about, well, he's a really good skier, because those are really good times. And he would probably have made the Swiss Downhill World Cup of those teams. But he might have slipped up. He might have skidded on one of the corner. And we don't know whether it was a slalom course or whether it was a downhill course. And to be honest, he probably isn't getting paid as much as the next person because his time. Get what I mean?
Yeah.
Do you recognise yourself when you're writing? Right? There is no evidence for any of those statements. That is purely you and your conjecture, what you think. The only thing I can say is that 68% of his times fall in those boundaries.
Well, less than 68%. Because,
Or more. Could be 11.
why would you round up?
Why not?
Because it's closer to 10.
But actually, if you work out the exact percentage for the normal distribution, it's not 68%, it's 68.4% or something like that.
Okay.
So it's all rounded. But my point is, well, you got my point, didn't you?
Yeah.
Just say what the evidence says and nothing more. All right? So this is how we can use those summary statistics and a different standard deviation, and we can make statements based on our normal distribution. All right? If I said to you, This is a more of a challenging question. If I said to you that he would qualify for the national downhill race team if at least 40% of his times were less than 6 minutes, would he qualify or not? This is a step on from what we're looking at here, by the way. Right, and you will need your calculators to work this one out using, well, you can't, sorry. You need your, did you get your emulator sorted out? Good, get that out.
Supposed to.
Okay, so.
Wait, what was the number to subtract by again?
2.18. So we've got 8.6 mean and we've got 2.18 standard deviation. Now we've got our normal distribution bell curve. Okay. And I've said, this, by the way, is the type of question that I'd be posing my standard level diploma students. Right? So I know my mean is 8.6 and I know my standard. So what did I say? 40% of his times below 6 minutes. So which half of the graph am I looking at? The bottom half. So I'm looking at this, okay? We know his runs are normally distributed. So I've got 6 minutes here. Now that's the boundary. He needs 40% below that time. Yeah? So that means this region here, do you remember we worked out the probability of within certain regions using your calculator? Remember doing that? Using your normal CDF?
Oh, yeah.
Remember doing that? You've used it before. Right, so what I'm after then is this hopefully is 40%. But what actually is it? Do you remember how to do it?
Yeah.
So we go for
Wait, what was the lower boundary?
normal CDF. Okay. And now here's a question for you. As you've already asked, what is the upper boundary? 6. What's the lower boundary? Okay, so in this situation, the lowest it can be is 0.
You can't do it in 0 seconds.
But this graph goes on forever. Now, the calculator doesn't know this, so what it needs to do, it needs to know that it will happily go into negatives. Now, we need it to consider all of the regions. So what we actually do is we want to actually go all the way to negative infinity. A good way to do that is to put negative 1, lots of zeros.
CDF.
Normal CDF.
What is that? Just distribution? What's normal CDF?
Cumulative distribution. Cumulative distributed frequency. Alright?
I can put negative infinities to be better.
Can you put negative infinity? I don't know, we never did. I just put a really big number, negative.
I don't think he would make the team.
So what is if it's normally distributed and his mean is 8.6 and his standard deviation is 2.18, what would that be? Did you work it out?
11.6.
11.6%. So
I
not the 40.
No, but I did 0 as the lower, so I'm doing
Or,
it again.
I'll try it again and see how much of a difference. It might not make an awful lot of difference.
11.65.
Yeah, that's what I got.
11.65%.
So 11.
So,
How'd you get that?
use the calculator. That's the thing. I can only say you've got to use your calculator. That's what I was trying to get. What happened to your emulator on your computer?
My computer broke.
I didn't do that.
What did you get?
41%.
41%.
I got 11.65 again.
So let me.
Wait, did you go as the as the lower one? Did you do one with like dozens upon dozens?
Did you do a minus?
Yeah, that's what I did.
Yeah, that's fine.
So let me have a look. So on mine, this is the older version of the calculator. I'll tell you what, I might have. At least if you use this one, it's not the one that. That's the only two I've got. Two different versions. You sit next to someone, yeah. So with this one, look, I'm going to go for.
January. 12 instead
It's
of
11.65.
Say it again.
I did extra one for the standard deviation is 12.
So guys, just to show you on my screen, I've got normal CDF on this calculator. So, Ethan, I'm going to go second and vars for distribution. That gets me normal CDF. Put on that. My lower boundary is already at -1 times 10 to the 90. That's a really negative number. And I'm going to put my upper bound as 6. My mean as 8.6. And my standard deviation is 2.18. And I know if that's the case, that 11.65% of his times were quicker than 6 minutes, right? He had to have 40%, so does he make the team? No. How could he improve? What would he have to, which number would we have to change?
His upper bound.
Well, that's set by the teams.
Oh,
His mean would have to change, wouldn't it?
oh,
Yeah?
yeah.
We'd have to bring his mean much closer to the 6 minutes. Okay? Because at the moment he's only got 11% and he would have to have 40% to make it. Alright? Stop this. Did you see